In this video, the third video, we are going to be introducing what is referred to as Raoult's law and how it is applied to ideal mixtures. And so, as I said before, we want to look at the binary mixtures, let's say, of water and alcohol. And so an ideal mixture is one in which it does obey Raoult's law. Different examples of ideal mixtures are shown here. Various types of liquids that's blended together. When you do have any type of solution and mixtures of various different fluids, you have intermolecular forces that are acting, and basically the smaller the intermolecular force that's acting among the various liquid molecules, the more the molecule will be able to escape at any given temperature. So one can think of the evaporation process or the saturation pressure above a surface of a liquid as being directly related to the intermolecular forces between the molecules in the liquid phase, and how that is a function of temperature. When you have a second liquid, the same thing holds. You have the second liquid here shown as red molecules, and again the intermolecular forces acting on those molecules then will give rise to its saturation pressure or its tendency to leave the surface. Now when you have a mixture of red and blue, you may think that only half as many of the molecules be escaping, but primarily what happens is that you will have a proportional amount of the various molecules escaping. And so the forces, the red molecules will still have the tendency to escape as before, and the blue molecules will also have the same tendency. And so what Raoult's law tells us or explains to us for an ideal mixture is that the partial vapor pressure, so whenever you have a mixture of two substances, you still have a vapor pressure over the entire surface, but part of the vapor pressure is associated with one of the fluids, and the other vapor pressure is associated with the other fluid. And so each fluid, whether it's A or B or blue or red, has a vapor pressure above it. That would be the vapor pressure as if it was only there. And the total vapor pressure then for the entire mixture is going to be then the addition of the two. And so what Raoult's law basically tells us for an ideal mixture is that if we have a value of X, which is, in this particular case, it's the mixture amount, it is the mole fraction of the two separate components, we find that when we have a mixture of A and B, it turns out that the partial pressure of each of those is going to be related to the mole fraction of the individual times the what's called here the the partial pressure if it was there by itself. Okay, so if we had a mixture of A and a B, the first thing we would look at is we'd say, okay, if it was A and it was at a temperature, what would it be its partial pressure? And that is this that super zero. Likewise, if we had B and it was by itself at a temperature, what would be its pressure? And this would be its partial pressure. And so when you put them together then, you proportionate the partial pressure for each of the individuals based on the amount of each that you have. And so, for instance, if you have half and half moles of A and half moles of B, what you would find then is you would take the partial pressure of A, take it by a half, the partial pressure of B, take it by a half, and then those are the partial pressures for the A and B combined that you would then add together for the total pressure. And so that is the definition or the statement of Raoult's law. And again, the mole fraction of a component is just the moles of that component over the total number of moles. So let's look at a really quick example. Let's suppose that you have 2 moles of methanol and you have 1 mole of ethanol at a particular temperature. And let's assume that the vapor pressure of pure methanol is 81. And the vapor pressure of pure ethanol is 45. And so they're giving you these 2 values here as if they were all by themselves at that particular temperature. And so in this particular case, you have this mixture of 2 to 1. What you then determine is that the partial pressure of the methanol is going to be 2/3 times the 81, and the partial pressure of the ethanol will be 1/3 times the 45. And so ethanol contributes 15 and methanol contributes 54. And so above that solution, that mixture, one would have a vapor pressure that was 69 kPa. And so, again, if it was all methanol, it would be 81. If it was all ethanol, it would be 45. And we have this combination, and that is the definition of Raoult's law. And so, based on the definition of Raoult's law that we just looked at, we could actually plot that by plotting on the x-axis one of the mole fractions. And in this particular case, if we were to plot from 0 to 1, the mole fraction of component A, and then on the y-axis, if we were to put the vapor pressure. Basically, over on the left-hand side here, if all we had was A, the vapor pressure of pure A would be this amount here. And then any mole fraction less than 1, we see that there is a proportional decrease in the vapor pressure going down to 0. Now on that same chart, we know that if we have a mixture of 2 components, we know that if the other component is B, over here at this side, we have all B where we have no A. And at that particular point, we would have the vapor pressure of pure B. And then over here on the right-hand side, where it's all A, we recognize that that would be no B. And so Raoult's law says that the vapor pressure contribution due to B would be decreasing in this fashion, just like we saw the vapor pressure due to A increasing in the same fashion. And so basically this is Raoult's law, wherein the mole fraction is obtained for any mixture. And so by adding those 2 together, we then have the blue line that represents the total vapor pressure of the mixture. And that consists of a portion due to A and a portion due to B added together to then be the vapor pressure at that particular mole fraction ratio. And so this then shows us description on a graphical direction, Raoult's law. Now, as we proceed further, we have vapor pressures associated with the substances. We know that vapor pressure and boiling points are related to each other. And so if we, instead of instead of starting with this equation, this plot here, if we were to say that when we had a high vapor pressure of B, that corresponds to a volatile substance that has a low boiling point. Likewise, if you have a vapor pressure of A, that corresponds to a less volatile substance with a higher boiling point, because vapor pressure and boiling point are inversely related to each other. And so if we were wanting to then replot this curve, we would then see that if we had all of A, we would see that the boiling point of pure A would be up here, which is less volatile, higher boiling point, lower vapor pressure. Likewise, for pure B, its boiling point would be down here because B is more volatile, has a higher vapor pressure, and therefore is a lower boiling point. And so the two endpoints look like that. And if we were to then discuss the concept, if we were to look at then the saturation pressure versus temperature curves, we would then be able to trace then what the line looks like in between, and that line would now take on this blue line. It turns out, and if you look at the the math and the information behind that, it's not a straight line, but rather a curved line. And so now we see on a boiling point basis, we see the boiling point of a mixture, which is related to the boiling point of the two components. The lower the boiling point, the more volatile that particular component is, and the higher the boiling point, the less volatile that is and the less amount. So we still can keep in mind boiling point and vapor pressure contributions. And so that then is the curve that we're looking for. Now, the next step is to decide what happens whenever we have a solution at a given mole fraction ratio. It has a boiling point, let's say right here. What is the condition of the vapor right above that surface? Well, the condition of the vapor right above that surface at that temperature is going to be heavily consisting of the more volatile component, B, and less of the less volatile component, A. And so we can then translate that. If we start off with a liquid with this composition, we then recognize that what actually is sitting above that interface is a vapor that has more A than it has B. And so, I'm sorry, it has more B than it has A, because B was more volatile. And so this is, it would go from, for instance, if this was a 2/3 to 1/3 mole fraction of A and B, it might go to 1/3 to 2/3 B. And so we go from this point, which is the composition boiling point of the liquid, to the composition same boiling point of the vapor. And so that that red point, or that purple point now, pink point I guess, can now be traced, and what we now have for a mixture of two pure substances, we now have a second line that corresponds to the composition of the vapor sitting above the liquid at a given temperature. And so this line is very important here. So now how do we use this? Well, let's say that we start off and we have a liquid that has a certain concentration of A and B. That's this point here, C1. C1, or that liquid, will have a boiling point that will be T1, and what comes off of the surface at this particular point then is vapor, and what we're going to find is it's going to be more B than it is A. And so just what we discussed is that, the more volatile component is going to come off greater than the less volatile component. And so what will be sitting above the surface then of that particular composition will be a composition C2. And so now we have a vapor that has more of B than it had of B when it was a liquid. Now, if we allow that to condense to a liquid, it then would have, we would then be down at this particular point. We then would have a liquid that is at that particular point. Now, if we can somehow separate that from the previous liquid, now we have a liquid that we can now boil, at a temperature, a lower temperature, and what will come off of that liquid will be over here. That will be more of the more volatile component B and less of the less volatile component A. And so what happens is we eventually, by doing this fractional distillation, we boil and then reboil. We boil, we condense, we reboil. And as we do that, we're driving the vapor to a higher and higher level associated with the more volatile component. And that's what happens in the distillation column. We start off with a mixture of water and ethanol, and that mixture might only be 15% ethanol. And so it might be way down here as 15% and 85% water. But we know that the ethanol has a higher volatility, and if we can somehow cause the system to boil and then to condense and to reboil, condense, and we can drive the vapor on top all the way up to a higher and higher percentage of the volatile component. And that's what is, being discussed here. And that finishes up this particular section dealing with the fractional distillation.